Imagine a world where robots anticipate our needs before we even utter a word. They brew our morning coffee just the way we like it and suggest solutions to our daily problems. This isn't a distant science fiction scenario, it's an emerging reality, thanks to artificial intelligence or AI. At the heart of AI is something that mimics the human brain's capabilities: neural networks. Neural networks are the silent operators behind many technologies we use today, from voice assistants to facial recognition systems. Just like our brains process a multitude of sensory inputs and make decisions, neural networks in computers analyze data and provide outputs. In this essay, we will explore how these networks work and how they echo the processes of the human brain. By the end, you'll see just how much our digital counterparts mirror our own cerebral functions, and what this means for the future. As we embark on this journey, consider how understanding these networks might transform your view of technology. The human brain is a biological wonder consisting of billions of neurons. Neurons are tiny cells that communicate with each other through electrical impulses and chemical signals. Each neuron can connect with thousands of others, forming a vast network that processes information at incredible speeds. This network manages everything from breathing to complex thought processes, making the brain a true multitasking marvel. Neurons communicate at junctions called synapses. When a neuron receives enough signals, it fires an impulse to its connected neighbors, passing on information. Drawing a parallel to artificial neurons or nodes in networks, we see a similar process. Just like biological neurons, artificial neurons receive inputs, process them, and generate outputs. By understanding the brain's structure and function, we gain insight into how neural networks are designed to replicate these extraordinary capabilities. Neural networks might sound complex, but at their core, they are beautifully structured systems. They consist of layers: the input layer, hidden layers, and the output layer. Think of this setup as a cake with multiple tiers, each layer playing a crucial role in processing information. The input layer receives data, the hidden layers transform it through a series of operations, and the output layer delivers the final result. Within each layer are nodes, analogous to neurons in the brain. These nodes are interconnected, and the connections between them are assigned weights. Weights determine the importance of inputs, much like a teacher assessing which student contributions are most relevant in a class discussion. Activation functions in nodes act like gatekeepers, deciding whether the processed information should be sent forward. Together, these components form a sophisticated architecture capable of learning from data and making informed decisions. Section 4. How neural networks learn. Neural networks learn through a process known as training, which involves adjusting their weights and biases to minimize errors in output. The primary method for refining these networks is called backpropagation, a technique that tweaks weights to reduce the discrepancy between desired and actual outcomes. During training, a dataset is fed into the network, and the output is compared against the expected result. If there's a significant error, backpropagation kicks in, adjusting the weights across the network in small increments. Different learning styles are employed depending on the task. Supervised learning uses labeled data to teach the network, providing clear examples of inputs and outputs. Through these learning processes, neural networks adapt and improve, showcasing their ability to learn from experience. Section 5. Types of neural networks and their uses. Neural networks come in various forms, each tailored to specific types of data and tasks. Feed-forward neural networks, or FNNs, are the simplest type, where data moves in one direction from input to output. They excel in pattern recognition tasks, such as handwriting recognition. Convolutional neural networks, or CNNs, are designed to process visual information, much like the human visual cortex. They are widely used in image and video recognition, where they can identify objects within photos, enable facial recognition, and even power augmented reality applications. Recurrent neural networks, or RNNs, are specialized for handling sequential data, making them ideal for tasks like language translation and speech recognition. Unlike FNNs, RNNs consider the context from previous inputs, allowing them to understand sequences and time-dependent data. Each type of neural network is a powerful tool in its domain, showcasing the versatility of these models in tackling diverse challenges across various industries. Section 6. Real-world applications of neural networks. Neural networks are not just theoretical constructs, they underpin many technologies we interact with daily. In image recognition, for example, they enable smartphone cameras to differentiate between faces and backgrounds, enhancing security features like facial unlock. Similarly, in autonomous vehicles, neural networks process vast amounts of data from sensors and cameras to make real-time driving decisions, ensuring safety and efficiency. In natural language processing, neural networks power chatbots and voice assistants, allowing them to understand and respond to human language. Financial institutions use neural networks for fraud detection, analyzing patterns in transactions to identify anomalies that might indicate fraudulent activity. These examples highlight the profound impact neural networks have on our daily lives, improving efficiency, security, and convenience across various sectors. Section 7. Future implications and ethical considerations. As neural networks continue to advance, they promise even more transformative changes in technology and society. Future developments could lead to more intuitive AI systems that can predict and respond to our needs with almost human-like understanding. However, this power comes with significant ethical considerations that we must address to ensure responsible AI development. One of the key challenges is ensuring transparency and fairness in AI systems. As neural networks become more complex, understanding their decision-making processes becomes harder, raising questions about accountability. It's crucial to develop methods to interpret these systems, ensuring they do not perpetuate biases or make unfair decisions. By considering ethical implications, we can harness their power to create a future where technology enhances human life while respecting our values and rights.